Hello, my name is Joshua Goldbard. I am the founder of MobileCoin, which is a cryptocurrency designed for everyday use. We're really excited to share with you a talk today that is entitled Why SGX, which is a discussion about secure enclaves and how we use them at MobileCoin. Before we begin, I'd like to introduce an artist. His name is Manny. He is based in Concord, and we're thrilled to support the arts and share his music with you today. Can we bring Manny in, please? Wonderful. Manny, feel free to take it away and play a song for us.
All right, thanks Josh for the quick intro. Hi everybody, my name is Manny. I'm gonna be playing some music for you guys. You can catch my music on Instagram at ORCHKEYSTRA _music, music. I will be playing a little bit of Beatles for you guys called Imagine, and here you go. Thank you.
Thank you so much, Manny. That was really wonderful. I really appreciate you sharing your music with us today.
Thank you, Josh.
Can
Thanks
we?
for having me.
Thank You're so welcome. Can we bring Sarah in? Wonderful. I'd like to introduce Sara Drakeley. Sara Drakeley is an infrastructure engineer here at MobileCoin. She is one of our senior developers, and she helps us to deal with a lot of different things. Recently, Sarah has been promoted to a manager at MobileCoin, and we're super excited to share her talk today on the subject of secure enclaves. Sarah, take it away.
Great, thanks, Josh. Thanks, Manny. That was absolutely beautiful. Hey, everyone. Thanks for tuning in. I'm Sarah. We're doing a series of talks on MobileCoin technology, and today I'm going to be talking about why we use SGX at MobileCoin. MobileCoin is a distributed system. There are several different types of participants, and the goal of the overall system is to enable peer-to-peer transactions. At the core of the system are these consensus validator nodes. Anyone can join the network as a validator, and we use Byzantine fault-tolerant consensus so that the nodes in the network come to agreement on whether a transaction is valid. The consensus validators are the servers in our system that use SGX. So then once the consensus validators agree that the transaction is valid, then they write that transaction to the ledger, which is distributed widely. And from that distributed ledger, clients can scan for their transactions in order to check their balance and to construct new transactions. So that's overall what the whole MobileCoin system is doing. Now, SGX is a new technology that allows us to do really powerful things in cryptocurrency. We're going to show you how we use the properties of this technology to improve the trust and the function of the remote servers in the MobileCoin network. But also, SGX is not a silver bullet, so we're going to cover some important aspects of how to properly deploy SGX in the wild. So what is SGX? SGX is a product from Intel, and it stands for Software Guard Extensions. In short, SGX is a set of instructions that can be enabled on your CPU, which reserve an area of memory called an enclave. And that enclave can only be accessed by processes inside the enclave. Let's go into some more detail about what this means. So you can imagine when you have a remote server with SGX enabled, you have a trusted enclave region, and then you have the untrusted region. That SGX-enabled hardware provides that specific instruction set to interact with the enclave. And this instruction set allows you to do things like initialize the enclave and then interact with the running enclave, so sending data in or getting data out. And inside the enclave is a reduced instruction set. So for example, certain IO operations are restricted. Everything that happens inside of the enclave is happening in encrypted RAM. So the processes inside the enclave cannot be accessed by any code outside the enclave, even processes with higher privilege levels or the hypervisor. And so this means that if you have access, if you have physical access to that remote server, you can't see what's going on inside the enclave. It's completely obscured to you. So encrypted RAM and SGX instructions provide confidentiality. Another feature of SGX that's really great is that the memory pages in SGX, those are handled by untrusted. And so this allows you to be able to load memory when you need to. However, this would be a concern that untrusted is handling those memory pages. That could be a concern because what if untrusted is modifying them in some way? So SGX uses a cryptographic primitive called a MAC, a message authentication code, for each memory page. And that allows the enclave to know when any memory has been tampered with. So tamper-proof memory access provides integrity. At the core, SGX changes your assumptions about remote computing. In the typical remote computing model, you have a client application and you have a remote server, and you're sending some requests and communication from the client application to the remote server. Typically, you would use something like transport layer security, TLS, and public key infrastructure, PKI, to encrypt and communicate, to encrypt and authenticate your communication. The problem is that any piece of software could be running on that remote server. Your chain of trust is limited to the certificates associated with the domain name of the remote server. And that's actually great. In most cases, that's just fine. This is how most of the internet functions for remote applications. But we can do better. And this is important, especially for a distributed system where anyone can join. To understand how SGX improves on the remote application model, we have to understand this term trusted computing base. So the TCB is the set of all hardware, firmware, and/or software components that are critical to a computer system's security. In the typical remote application model, the remote server is part of your trusted computing base. It's both the server, the application, everything else that's running on that server, as well as you need to trust TLS and PKI are guaranteeing that you're talking to the correct machine. SGX shrinks your trusted computing base when talking to a remote server. So now all you have to trust is the enclave itself, as well as the hardware that enables the enclave to exist. But how does the client know that it's talking to the right enclave? How does this trust actually work from a technological perspective? So one feature that enables this from SGX is the ability to take the measurement of an enclave. So what this measurement is it's a measurement of all the software that's going to be running on that enclave, as well as the memory on enclave startup. It also verifies some other aspects of the trusted computing base. So it can look at some of the configuration, like whether the GPU is enabled, or it can look at what version of the microcode is running. And it does look at all these things. And then all of this data produces a hash called the measurement. And that measurement is sent to a third party for verification. So this third party, the Trusted Attestation Service, then verifies the measurement and the data from the enclave. And it verifies that it was signed by the enclave's provisioned key. And then that attestation service signs that whole package, and it sends back this report that verifies that the measurement was valid and produced by a properly configured enclave. That signed report can then be sent to the client. So the client is going to be preloaded with the measurement that they expect. But how did the client get that measurement? They either received it from the party who's running the enclave, and maybe they trust that party to tell them what measurement to expect, and that works great. But even more powerful is that if the enclave code is open source, and MobileCoin is open source, so you can do this, then the client can actually pull down that enclave software and build it themselves and get that measurement. And you can see what that measurement should be. And then you can verify that the enclave that you're connecting to is running the very code that you can look at. So after establishing that that measurement is correct, the client and server create an attested channel through which they can send encrypted communication. So one thing to note is that the attested channel, it can't provide that administrative identity that you get from PKI. So it's still best practice to wrap your communications in TLS with PKI. All right, so to understand what this is getting us, we need to talk about this concept of non-repeatability. So at a high level, non-repeatability is that the author cannot dispute the authorship of the associated content. So this is what a signature gets you. It's this linkage of the content to an identity. And non-repeatability in digital security provides both the proof of the integrity and the origin of the data, as well as the sense that the authentication is genuine with high confidence. And so that's what the measurement and attestation get us. It provides this authenticity. Okay, so that's the baseline. That's the general why for SGX. This is why anyone might want to run SGX in their distributed system. But now let's talk about the benefits of how SGX is used specifically in the MobileCoin protocol. So with attested connections and enclave measurements of our open source software, then the nodes in consensus can be confident that they're talking only to other nodes running the exact correct version of MobileCoin. And the clients also have confidence that their transaction submissions are private. So the operations where integrity and confidentiality matter are where we use SGX. And so that's for consensus and validation and for submitting transactions. So at MobileCoin, we run the Byzantine fault-tolerant consensus. And to understand what that is, it's a whole thing, but I'm just going to briefly talk about what a Byzantine fault is. So a Byzantine fault is when a component in a distributed computer system appears both failed and functioning at the same time, depending on who's looking, when they're looking, or where they're looking from. The benefit of Byzantine fault-tolerant consensus is that consensus can be reached even without removing the Byzantine actor. So typically in a distributed system, if you're not Byzantine fault-tolerant, then when there is a Byzantine actor, everyone in the network has to come to consensus that that actor needs to be removed, but not so in Byzantine fault-tolerant consensus. So what is an example of a Byzantine fault? So it can be something that's not malicious. It could be that someone has a spotty network, and in that case, they look like they're participating sometimes, and sometimes they seem to be not responding and not making progress. That's something that is a Byzantine fault, but that's not something SGX can help us with. Something SGX can help us with is if a Byzantine actor could be someone who's trying to intentionally run software that doesn't follow the MobileCoin protocol. So if they're trying to run a malicious enclave that would not validate transactions, or that would try to, as you'll see, reduce the privacy of the protocol, if they're running that enclave can't actually connect in with the other nodes because they won't attest. They'll have a different measurement. And so they're just not even allowed to participate in consensus. In that way, SGX and consensus prevents certain Byzantine actors. All right, so next we're going to talk about how SGX improves the privacy of our transaction protocol. In order to understand how, we have to go a little bit into the background of how transactions work. So basically, blockchain transactions consist of inputs and outputs. So how can we visualize this? You have an input, which is the output of a previous transaction. So let's say you have Alice sent 5 MOB to Bob. So that's now this unit that Bob has. He has this 5 MOB chunk. And if he wants to construct a new transaction, he has to consume that whole input. So he has to consume that 5 MOB. Maybe he wants to send 3 MOB to Carol, but then he has to also send 2 MOB back to himself. So he consumes that whole transaction in order to create 2 new outputs of different amounts. And if we follow this through, as many transactions are added, we start to get this transaction graph as inputs are consumed to create new outputs. And the MobileCoin transaction is designed to provide privacy for the sender, the recipient, and the amount of each transaction. Our first tech talk in this series was by Matt Faulkner, and he went into detail about the cryptographic components of the MobileCoin transaction. I encourage you to check out that talk for more details about how this all works. For the purpose of understanding how SGX improves the privacy of MobileCoin transactions, all we need to dive into today is a little bit more about how ring signatures work. So one way you can start to think about it is that previously we said Alice sent 5 MOB to Bob. Once we have redacted these elements of the amount and the recipient, then it's, Alice sent 5 or redacted MOB to redacted recipient. And then with a ring signature, it's sort of like saying Alice or Bob or Carol or Dave sent some amount of MOB to some recipient. But that's not quite what's happening. So a more proper illustration is something like this. So any one of these 4 inputs is equally likely to be the input that created these 2 outputs. And then from there, if you want to create some more outputs from those, then you have to recruit some other transaction to be part of your ring signature. And then you can use that whole input package is then potentially creating the outputs of the next transaction. If this is hard to follow, exactly, that's part of the point. But something we have to understand with this sort of construction is that there's a difference in the quality of the cryptographic security of a ring signature, say, versus a one-time transaction. So with a ring signature, you have something that's privacy via obfuscation. The components have a probability of a relationship, and this allows you to, it gives you deniability. So any one of the inputs that was recruited for this transaction is only probably likely to be part of the real input. So yeah, so you only have this one out of however many inputs likelihood of being the real input, and you can't prove that you were or that you were not. And this is in contrast to privacy via cryptographic security, which is that the components are computationally indistinguishable from random. So this means that for however long that random string or random number is, it's equally likely to have come from the whole space of random inputs that would have produced that random number. Okay, so how does this play out? How does SGX come into this? So as we start to trace these inputs through in the transaction graph, you have these input-output relationships, these probabilistic relationships. And over time, you're going to be using those outputs to construct new inputs, and you may have to use multiple outputs in order to construct a new transaction. And with a large enough transaction graph, you can actually perform statistical analysis and reveal sender-recipient relationships. So ring signatures provide deniability and obfuscation, but we can do better. And it's important to say that this is already state-of-the-art for privacy and cryptocurrency. So ring signatures, as well as all of the other aspects of the transaction protocol, it's great. That's already state-of-the-art. But with SGX, we can make it even better. And how? So how is this going to work? Well, SGX allows us to delete the toxic waste of the inputs. So because we have attestation, all of the nodes that are performing consensus at the same time, they've all attested to each other, and they all are certain that they're running the exact same code. This is great because the reason why those inputs are necessary are just at that moment in time when that transaction is being validated, you have to validate that those inputs were really valid to be spent. And the enclaves do this, and then they can write the transaction to the ledger. But those inputs are never needed again. And so you could actually delete the inputs and not have to write them to the ledger. This is extremely powerful. So I'm just going to say it again. Because the nodes are all attested with each other and they know that they're running the same code, they know that they're doing the exact same validation. They also know that the code that they're running guarantees that they're going to delete those inputs. And so the result is that at the end of the validation, all of the consensus validators can write only the outputs to the ledger. That allows us to delete the relationships between the transactions. So there's no transaction graph analysis possible on the MobileCoin ledger. So transaction validation inside SGX enhances privacy. So we talked about what SGX provides to enhance the MobileCoin protocol, but now let's talk about what it takes to run SGX in practice. Because naively deploying SGX is not enough to ensure its security. You have to take some careful steps to use this technology carefully or correctly. All right, so we just talked about how transaction validation inside of encrypted RAM means that node operators can't even see those obfuscated transactions. But there's one wrinkle, and that's this idea of sidechannel observation. What is a sidechannel? A sidechannel leaks information. It allows the attacker to decode the data that would otherwise be cryptographically secure. The entire MobileCoin system can be thought of as a cryptographic protocol. And if there is a sidechannel attack possible on the cryptographic protocol, it means that somewhere it's possible to see some secret that is critical to the cryptographic protocol functioning. What's an example of a sidechannel attack? One example is a sidechannel timing attack. This is pretty. It's a common attack if you aren't being careful about how you construct your application. So the way this works is that if you have two requests that are the same size and you send them to the remote server, the requests might take a different length of time to complete. And this can be enough to determine secrets that are either in the request or on the remote server. To protect against timing attacks, every secret handling component of your cryptographic protocol and the trusted computing base must be constant time. And one important thing about that is that it's not that your whole application has to be constant time, but anything that's touching secrets must be. All right, so what's another class of sidechannel attacks? Well, this is microarchitecture attacks. And this is where information can leak due to the underlying hardware. This encompasses everything from power consumption to the interface between the software and the hardware. I'll list off some recent microarchitecture attacks because they all have cool names. So you have things like Spectre, Meltdown, Plundervolt, SGX, load value injection, or using the GPU to read bytes in SGX. These are all examples of microarchitecture attacks. So how do you protect against a microarchitecture attack? Your hardware and TCB must be up to date with patches. And in our experience, patches are usually released a few weeks after an attack is published. And then you also have to make sure that you're properly configured. So there may be some requirements for your settings in the BIOS, for example, to disable hyperthreading or to disable your GPU. And so if those things are all patched and properly configured, and then the measurement can also take into account these configurations and the versions of your microcode, and can tell you whether your SGX setup is vulnerable. And the other way that you have to protect against microarchitecture attacks is that you often have to actually perform some mitigations in your own software. So this may be something like using LFENCE everywhere or not having code that branches. Okay, so now that we understand that sidechannel attacks are something that you have to include in your threat model, what does it mean for MobileCoin if there is a sidechannel attack against SGX? Well, in short, it may allow that attacker to see the transaction graph. So if the attacker has an exploit, they may be able to shine their magnifying glass onto the enclave and see those inputs as those transactions are being validated. And even though that's then written to the ledger without the inputs, that attacker would have been able to observe them in flight. But an important thing to note is that even in the event of a compromise, the transaction graph is only temporarily revealed via that side channel. So what that attacker is seeing is still those obfuscated ring signatures, which is already the state of the art in privacy on blockchain. But you're also only able to see it for that amount of time. So you can't see any transactions in the past that have already happened. And you actually, once it's patched, you wouldn't be able to see anything in the future as well. And so this preserves forward secrecy. And what's forward secrecy? It's the idea that you can protect past sessions against future compromises. In addition, there is no known transaction graph analysis attack on a partial transaction graph. So it's not even clear what the attacker could do with this partial transaction graph. But it is important to note that that is something that if you had an SGX exploit, that is something that you would be able to observe, is this obfuscated transaction graph for a short amount of time inside of the enclave. All right, but to kind of sum up that discussion, transaction validation inside SGX preserves forward secrecy. We started this talk with the question, why do we use SGX in our infrastructure at MobileCoin? And the answer is for the baseline of what SGX gives us, integrity, confidentiality, and authenticity, as well as to enhance our Byzantine fault-tolerant consensus. It gives us privacy that resists transaction graph analysis, and it provides forward secrecy in the event of an SGX compromise. So the final point to conclude this presentation is that the core MobileCoin protocol is sound. You can't do things like double spends, you can't mint coins, and it has state-of-the-art privacy. But SGX meaningfully enhances the core protocol, and it makes our whole system stronger. So thank you, everyone, for listening to this talk, and we're excited to field some questions.
Cool. Thank you, Sarah. That was really engaging. I really appreciate you putting all that content together. I know it's a lot of work. Thank you so much.
Yeah, thank you.
My first question is, I really think that SGX is an additive thing for distributed systems because it lets you have a smaller trust area on the server that you're connecting to. Can you talk about why it's so difficult to implement SGX and why we don't see it in like a ton of applications right now?
Sure. So SGX, it is the configuration aspect is one thing. You have to make sure everything is properly configured. You also have to make sure that your software is meaningful to be running in SGX. For example, if you write software for the enclave that has these timing attacks, then you're vulnerable to certain side channel attacks. But from an operations perspective of why is it so hard to run SGX in the wild, one is that there are not many cloud providers who offer SGX. And the ones that do, we absolutely love. So Azure is out there offering SGX, IBM has SGX, and that's great because then you can just start up a box and have SGX enabled on your remote server. But even once you have a box with SGX, you have to write software that's going to build and run properly. And it's a whole different set of hardware, right? So Intel has an open source library, but we want to work in Rust. So we've had to write all of the translations to be able to use the Intel C libraries in our Rust application. And yeah, there's a lot of layers to this. And actually, we're going to be having a future talk that goes way more into depth about the how of how we use SGX. And I think that will also illuminate some of that as well.
Cool. My next question is about the sort of obfuscation and the way that we deal with that. So I really appreciated this idea that even if SGX is compromised, that you still have this sort of like ring transaction graph. Can you talk a little bit more about the way that that works and the way that the forward secrecy works?
Sure. I could bring back up those slides, but I'll try to describe it. So the ring signatures, it's this idea that you have multiple inputs that each one is equally likely to have been the source for producing the new outputs of a transaction.
Yeah, and so it's like 1 of 8, right? 1 of 8
right.
Or 1 of 3 or whatever, how many you choose.
That's right. And so you are not, and it's cryptographically, the way that it's structured is that you can prove that one of these identities was, or one of these inputs was the one that created the output, but you can't prove which one. And so this comes from a paper called How to Leak a Secret, which is a fantastic paper that was sort of the introduction of ring signatures. And so, yeah, so we use these ring signatures. And then the problem with it is that over time, over a long enough time, you're using these inputs and you're consuming them to create new outputs. And eventually you'll have to use multiple inputs to create a new output. And once you start to do that, you might be able to do some statistical analysis and observe that these inputs may have been related because they were all used to make this output. And so there's also actually a great talk about this specific sort of vulnerability, and that's from Ian Myers. I think it's called Satoshi Has No Clothes, but I highly recommend checking out that talk as well. It kind of goes into a few different attacks that are related to this concept. And so once you have that full transaction graph, it's possible to do that statistical analysis. And then what SGX allows us to do for MobileCoin is that we can actually delete those inputs. And so you can't do that transaction graph analysis. And the reason why we can delete those inputs is because SGX is in the mix. So it's because all of the nodes that are doing this validation of the inputs are running the exact same code. Yeah. Yeah.
That's super cool. One of the things that I really appreciate about it is that in the case of obfuscation, like a partial transaction graph has never been successfully attacked as far as I know. And what I think is really cool is that when SGX is operating, the MobileCoin transaction set in terms of where we're obfuscating the transaction, it's the total set of transactions. And so that is computational indistinguishability, which is the highest cryptographic standard you can possibly have. And so I think that it's really cool that we have the ability to get there and to still have like a super fast operating cryptocurrency, because MobileCoin is really quick, right?
Yep. Yeah, MobileCoin is super quick.
Cool. So can you talk a little bit about the sort of like ways we work with attestation? Because I know that there's been like client to server attestation before. Signal sort of pioneered using that in a big consumer app, but I know that we do a little bit more than that, and so I would love if you could talk just a little bit about how we use SGX to have servers talk to each other.
Sure. Yeah. So we have two different types of attestation in the MobileCoin ecosystem, and one of them is client to server, and the other is server to server. And so a few details about what we do there. So it's still the same enclave measurement. And so both the clients and all of the nodes, they have preloaded that measurement that they should be expecting from their peers. And then once they connect, they do an exchange. And this is also something, so we're using the noise protocol for that, and it's really interesting. And I think James Cape is probably going to cover a lot of these details in his next talk. But so we're doing this authenticated key exchange, and then we can create that attested channel between the nodes. And so then it's almost as though the nodes are all running within the exact same enclave. It just happens to be distributed around these multiple servers. And then when the clients connect, they attest with the nodes. And one slight difference is that the peers have to attest bidirectionally. So they both have to confirm that they are talking to an enclave that is the right measurement, whereas the client only has to confirm that it's talking to a consensus node that has the right measurement. The node doesn't care what client is trying to talk to it.
Cool. Yeah, one of the things I love about this system is that it's a chain of trust that goes all the way back to the client, that the client can completely verify from end to end. And there really aren't that many systems out there that are structured this way. So it's super cool that we're working on something like that. I think the final thing that I want to talk about briefly, and this sort of hints at another call that we're going to have another tech talk. But one of the cool things about SGX is that it lets you trust a remote server in really interesting ways that aren't possible without SGX. And so I think one of the main things that I'm really excited about is giving mobile phones the ability to have access to the ledger without storing the entire ledger on their phone, and to do that in like a really fast way. I don't know if you want to like hint at that a little bit, because I know obviously we're going to do a talk about that in a little while, but I would love if you could just talk sort of briefly about what's cool about that.
Sure. So yeah, I'd love to hint at this. I think this is something that MobileCoin is doing that's really innovating in this space. And so let's see. So the idea is that you can have your phones not have to have the whole ledger. So can you have a service that can provide the ledger to you. And one thing you have to know about how MobileCoin transactions work is that the only way you can tell that a transaction belongs to you is that you have to apply your secret key material to that transaction. And that's the only way you can tell if that transaction is yours. So what you would imagine that you would have to do is you would imagine that you would have to stream that whole ledger to your device and be able to check every single transaction against your private key material from the whole ledger to understand which transactions were yours. But we've actually invented a better way. And so the dangerous way you could solve this problem, the way that we're not doing it, is that you could just give your keys to a third party and trust them to stream the ledger on your behalf. Right.
And that was originally the way that we were going to do it, but we just sort of decided that wasn't reasonable. And so, I think we spent a lot of time kind of thinking about, like, is there a different way to do this, Right,
exactly. And so the approach that we have, and Josh, I don't want to like describe too much.
I don't want to steal thunder. I don't want to steal thunder. I just kind of want to hint at it.
Okay. So the way that we're doing this is that we're going to have a fleet of SGX servers that are performing their SGX microservices that are performing different aspects of what you would need from your phone in order to gather the transaction material that you need to construct a transaction, as well as in order to get the materials in order to check your balance. And so all of those enclaves are then, extremely trusted because of all the reasons we've talked about. And in addition, we're going to be using an oblivious layer that helps you to conceal your transactions or to conceal your requests and what you're actually asking for when you talk to these enclaves.
Yeah, so I don't want to go too much into detail into it, but I'm really excited to talk about that. It's one of the ways that we think we're really innovating with SGX right now. So I think that's it for the talk today. I just want to thank Sara so much for spending time creating that deck. It was super interesting and really wonderful content, and I'm just really pleased that you were able to go over that. And also thank you as well to Manny, our musical guest from Concord. And thank you to Brady Forrest for being our engineer in the background, working on this and making us look good in the stream. So thank you everybody who watched, and we'll do another one of these soon. Thank you so much. Have a good night.